Hello and welcome. Today we are going to be looking at a TMUA style problem involving the number of solutions to a quartic equation. So we're given this quartic equation, x to the 4 minus 4ax cubed plus 4a squared x squared minus a is equal to 0. And we're asked to find the set of values for a for which this equation has exactly 4 distinct real solutions. So something that we might try straight away when we see a quartic like this is maybe we can factorize it. We don't have too many ways of factorizing quartics. We can either get lucky and spot a factorization, which is difficult here, or we can use the factor theorem. So maybe we can find a root. In this case, you can try out some values, maybe x equals 1, x equals minus 1. You could try out some multiples of a. But ultimately, after a bit of testing, most people will realize that that's not exactly the route that we want to go down. So what else can we do? Well, sure, the entire quartic is a bit difficult to deal with, but this section, which excludes the constant, is a lot easier to work with. We can factor out our x squared, and then our remaining factor is just going to be a quadratic, and hopefully we can factorize them. So a common trick for this type of question, where we have an annoying constant term, this minus a over here, is since we're only looking at solutions to the equation, we can add a to both sides and work with the remaining quartic that we're given on the left. So let's try this out. We're going to have x to the 4 minus 4ax cubed plus 4a squared x squared is equal to a. And now, as promised, we can factor out this x squared. In the remaining bracket, we're going to have x squared minus 4ax plus 4a squared, still equal to a. Now, this quadratic is a lot more approachable, and we can actually spot the factorization directly if we remember that a plus b squared in general is a squared plus 2ab plus b squared. You can spot over here that the x coefficient is 2 times minus 2a, and the constant term is minus 2a squared. So if we use the form above, we can realize that the factorization of this quadratic is nothing but minus 2a squared. If you're unsure about this, you can expand this out, and there are other ways that we could factorize. You could, for example, try to find a root and divide by that. So if you subbed in x equals 2a, you would see that this quadratic comes out to 0. Okay, so we have the factorization now. And we have a graphical way of thinking about our solutions to this equation. So this quartic is a lot easier to work with, and the solutions are going to arise when the quartic intersects with the line y equals a. So let's start off maybe by sketching our quartic. We know that the roots are at x equals 0 and x equals 2a. This is a positive quartic, and it has two double roots. So we know at a double root, we're going to get behavior roughly like a quadratic. So we're going to have this type of U shape. And since this is a positive quartic, we are able to read off the rest of the behavior. So it's just going to increase away from its roots. And over here, it must increase, but it must also come back down to grab this other root, x equals 2a. So we have some behavior like this. Let's plot on maybe our line y equals a. So that's going to be a horizontal line at a height of a. And this needs to have 4 distinct intersections with the quartic that we're working with. Now, what you can kind of see is that, well, firstly, anything at 0 or below doesn't work. So here we have 2 solutions, here we have 0 solutions. And also anything at or above the turning point won't work either. So at height, which is the same as the turning point, we're going to get 3 distinct solutions. And above that, we're only going to have 2. So what we want is a line like this red one over here, something which is between 0 and the height of the turning point. And that means to find the exact set of potential values for A, like this question wants us to do, it's important that we know the height of the turning point of this quartic. So how can we find that? Well, if we take a look at our quartic, we could just differentiate it and set it equal to 0. And that is going to work. We're going to get a cubic with a factor of x, so you'll be able to factor that x out and then solve the remaining quadratic. But there is actually another way. So we can notice that this quartic over here is the square of x times x minus 2a. And this is a quadratic. Now, quadratics are symmetric around their turning points, and that turning point is always going to be at the midpoint of the 2 roots when the quadratic does have roots. So let's maybe do a small sketch. This is a positive quadratic. The roots are at 0 and 2a. We have this type of U shape. And the turning point, which the quadratic is symmetric around, must be evenly spaced between these 2 roots. So that's going to be at an x value of a. Now, this quadratic is symmetric around the line x equals a, which means that the quartic is going to be as well, because it's just the square of the quadratic, and if you square a symmetric function, it will remain symmetric. This is helpful in this case, because if we can spot this, we can realize that the turning point must actually be at x equals a. If it wasn't, let's say, for example, it was to the left, then since this is a local maximum, the function couldn't possibly be symmetric around here, because it would have to go back up for that symmetry. And that can't work since this is a cubic, and at most it can make a W shape. It can't really wiggle any more than that. So we know the turning point is at x equals a, and we can now find the y value of that turning point by substituting into the quartic that we have. So the quartic is x squared times x minus 2a squared. So that will give us a squared times a minus 2a squared, which comes out to a to the power of 4. So this height over here is a to the power of 4. Now we said that we get a solution when a is bigger than 0, but less than the value of the turning point, which is a to the power of 4. So what we need is a greater than 0, and a to the 4 must be larger than a. Well, since a is positive, we can actually divide this inequality by a. That's not going to change the sign or cause any problems because a is positive. So that means that a cubed must be bigger than 1. And since 3 is an odd number, we can actually take cube roots, and this is equivalent to a being bigger than 1. Now, we did also have this extra condition that a must be bigger than 0, but we can see that this over here takes care of that. A is bigger than 1, then it's also bigger than 0. So we don't need that extra condition anymore. And our final answer is a is bigger than 1. So that means that the answer is option A. Okay, thank you so much for watching, and I'll catch you all in the next one.